All right, there's one more class of randomized optimization algorithms that is really attractive. It's very interesting to people. It has proven itself time and again, and it is this notion of genetic algorithms. So the main insight that's exploited in the genetic algorithm setting is this. So let's imagine we've got a two-dimensional space, and it's hard for me to actually draw a fitness surface over a two-dimensional space. So just kind of think of this as being one of those maps, those contour maps. And so imagine that we've got one dimension, that x now comes in these two different dimensions, and what we're trying to do is find the peak, which happens to be there. So what if we actually evaluate three different points? So these green points here, we actually check what the values are at these points. And what we find is that from this initial point, this green point here, if we increase on dimension 2, we get a better value. But it's also the case that starting from that point, if we increase on dimension 1, we get a better value. So maybe what we ought to do is take kind of elements of these two solutions, these two inputs, and combine them together and move out on dimension 1 and dimension 2, and maybe that will actually give us a good score as well. And in this particular case, it puts us right in the basis of attraction of the local maximum. So this turns out to be useful in many spaces, especially spaces that can be specified combinatorially like this, where there's these separate dimensions that contribute in various ways to the overall fitness value.
Okay, Michael, that sort of makes sense. But what does this have to do with genetics or algorithms for that matter?
Well, it's an algorithm in that it's an optimization algorithm. And the genetic part is because what we're going to do is we're going to build an analogy with biological evolution.
Analogies.
In particular, instead of thinking about these input points, these little green dots, we're going to think of them as each input point is like an individual, and a group of them taken together is like a population. It's really the same idea, but we're just giving it a different name.
Okay.
The idea of local search, where you make little changes to an input, we're going to now call that mutation, right? Where you take an individual and kind of tweak it a little bit,
Oh, like we did in the example we did before, where we defined the neighborhood as every one difference in every single bit.
That's right. So the mutations can happen along neighborhoods. It's the same kind of concept as that.
Okay.
And then, and you can see that there's the mutations happening over X, so I assume that you get X-Men.
I think that's a fair point. I like your science.
That's right. It is science. Those are all concepts that we were already using when we were doing these other randomized optimization algorithms. One thing that's different, though, is the notion of crossover. So what crossover does is it takes different points, like this green point and this green point, and instead of moving them just to their own neighborhood, it gives you a way of combining their attributes together with the hope of creating something even better. So that is where it starts to actually kind of deviate from the standard notion of local search or randomized optimization and gets us into something that feels a little bit more like evolution. So this is kind of like, dare I say, sexual reproduction, right? Where the two parents can actually form a new kind of offspring that, if you're lucky, has all the positive attributes of both of the parents, like my children.
And if you're unlucky, it has the worst attributes of the parents, like other people's children.
Exactly. And finally, what we were calling iteration before, in the context of genetic algorithms, we can call it a generation, because we're going to take a population of individuals and kind of, mate them together to create a new population of individuals. And we're going to, what we hope is improve iteration by iteration.
Okay, that makes sense. So if I can just push on this a minute, it seems like if it weren't for crossover, this is really like doing random restart, except instead of doing restarts, you just do them all at once because we have parallel computers.
Yeah, I think that's fair. I think that's quite fair, actually.
Okay, so then the thing that makes it more than that is crossover, that somehow these parallel random searches are bleeding information back and forth. Oh, maybe bleed's the wrong.
Yeah, you don't want to get too biological about this.
Yes, so they're sharing fluids, metaphorically, with one another and conveying information that way, just the way genes do.
Right, and so that's this sort of interesting concept that now we have information not just in the individual, like we're moving that one individual around and trying to find better and better solutions, but the population as a whole represents a distribution over individuals, and that distribution might actually be a useful thing to guide the search for higher scoring individuals.
Okay, that makes sense.